lecture series for this year. I'm very happy to have a good turnout. The idea here is to have lectures on topics that might be of general interest in the area of machine learning, in both theory and applications. And our first speaker is Rishi Kondor, who is a research fellow at the Gatsby unit at UCL. Rishi studied mathematics at Cambridge and then went on to CMU to get a graduate degree in computer science, and then Columbia University. And we're very lucky to have him back in the UK now and close by to us here in London, and I hope that he'll interact with us closely. Rishi has been doing very pioneering work bringing together ideas from group theory into machine learning, and I hope you get a great taste for this interesting area of research from Rishi's tutorial today. So, thanks.
Thank you. Okay, thanks very much, Zubin. So, as Zubin mentioned, this is a bit like bringing group theory back from where I got it from in the first place. It was more than a decade ago when I studied it here at Cambridge, and for a while afterwards I thought I would never really use it much. That seemed like one of the more abstract parts of the math tripos. I progressively went into more and more applied fields through physics and then computer science, machine learning. And then I discovered that similar sorts of ideas of symmetry and structure appear even in machine learning. So now I'm trying to combine these two fields, and it's a great honor to be able to talk about group theory right here in Cambridge again. Okay. So this is the motto for the talk. A famous verse from William Blake. Very few things can express the power and also the beauty of symmetry and structure in mathematics more than these couple of lines. All right. So let us start in the abstract, talk about what a group is to a mathematician, and then see how it links up to our ideas of learning in computer science. Okay, so one way to think about groups is rather abstract, and it just starts with a set and a certain operation denoted with a multiplication on that set, which satisfies specific axioms. So these are the famous group axioms. First one of them is closure. That is, if you take any two elements from the set and you apply the multiplication operation to them, you must stay inside the set. Next one is associativity, which is rather, from a mathematician's point of view, is rather a sort of minimalistic requirement of a binary operation. It just has to do with the order in which you group the factors in a product. Then the existence of an identity. Well, without the identity, you are kind of stuck. It's a really fundamental thing to have in any algebraic structure. And really the only one which only requirement which is substantial and makes groups into what they are is the existence of inverses. So that just says that for any group element G, there must be a corresponding G inverse, such that if you right multiply or left multiply G with that inverse, then you get back the identity. So this is like you can undo any operation. The reason mathematicians are interested in groups is because of their inherent structure. So these four, at first sight, apparently really simple and minimalistic axioms capture something fundamental about algebra, about what algebraic operations are, and then you can study what sort of structures these axioms give rise to. This is a really fundamental problem in mathematics. It kind of fits into this spectrum of algebraic objects, but in some sense groups are canonical even within that sequence because of the canonical nature of the axioms. But for applied science, be it physics or machine learning, groups don't occur so much in their abstract manifestation as here, but as manifestations of essentially symmetries. So by symmetry, I mean something like the symmetries of an object, like the icosahedron here. So you just consider all possible transformations of this object, all possible rotations, which take this object into itself. So they permute the vertices, but you're still going to get back the same object in the same position. Now, what is the relationship between groups and such symmetry transformations? Well, let's think about what symmetry transformations like this really are, how they form a system. Well, at the most fundamental level, symmetry transformation is just an operation on some underlying object, right? So when I started out studying mathematics, this was even before Cambridge, I was told to think of functions as meat mincers. This has been one of the most fundamental ideas that have stuck with me all through these years, and I found really useful in my research today, I can tell you. So I'm going to use meat mincers throughout the talk. What happens is that you put in something like the icosahedron, you turn the crank, and out comes a rotated icosahedron, right? This is the operation. This is going to be our group element. What we are interested in is how these meat mincers combine with each other, right? How the operations form an algebraic structure within themselves. So what can we do with these meat mincers? Well, the obvious thing to try, I'm not sure if anybody has done this with real mincers or real meat, is to put them in series, right? So what comes out of one meat mincer? Well, you stick it back into another meat mincer. And then ask yourself, what does this combined meat mincer do? Well, this is just another operation, right? Again, you put in an icosahedron, out comes an icosahedron as the combination of these two operations. So you can call this combined meat mincer the product mincer G1 times G2, okay? So this is going to be our group operation. This is the link between the abstract operation on the set G and how groups actually operate on real objects such as the Platonic solids, okay? So the question is, what are the requirements that we impose on this operation, and what sort of properties do those requirements give rise to? Well, first of all, as I just said, if you take any two operations, then their combination must also be in the set, right? So if you have one symmetry of the icosahedron and you follow it by another, one rotation followed by another rotation, then the combined rotation is just another rotation, so it must be in the set of all symmetries or all possible rotations of the icosahedron. Okay, so this is the closure axiom of the groups. Now the second requirement is if you change three of these operations, then the two ways in which you can break that down, as in first combining operation 1 and 2 and then following it by 3, or first combining 2 and 3 and then preceding it by 1, well, these must give rise to the same combined operation. So no matter which of these two things you do, you must get the same product, you must get the same product mincer. Right? So this is associativity. Associative is really fundamental to how we think about operations. It's not some abstract algebraic concept. It's inherent in how we think about things such as these functions represented by the meat mincers operating on their arguments. Now, the identity operation is just going to be the rather boring mincer which doesn't change what you stick into it. And then the only thing that is kind of unusual in the world of real mincers is that you can also unmince, right? So for any group and any transformation, you must also have its inverse in the same set. But if you don't think about meat and mincers, but you think about, say, the icosahedron, this is an obvious requirement, right? So if you can rotate the icosahedron from one position to another, then you must also be able to unrotate it, or affect the inverse transformation. Okay, so this was just to demonstrate that the group axioms can be expected to occur naturally anywhere where you have a set of operations acting on some underlying objects, in particular when they capture symmetry. So this is the reason that group theory has been fundamental to 20th century physics. People realized that it's a really powerful technique to exploit the kind of prior information or hunch that we have about nature, about the large-scale structure of nature, about the fundamental invariances in nature, and that just looking at the symmetries themselves can lead to really powerful statement about the nature of physical laws. So this was physics. This was one of the main driving forces behind physics, and say well, throughout the 20th century, but say starting in the 1930s. The question I'm going to address in the talk is how to do something similar with data. So when we don't have physical systems going in and out of these operations, but when we're looking at the invariances of naturally occurring data. So we're going to be looking at various groups. But we're going to be looking both at discrete groups and continuous groups. We're going to be looking at finite and infinite groups. One distinction that we are going to have to make is between commutative and non-commutative groups. So this is a fundamental thing. If the group operation is commutative, that is, if it doesn't matter which order you chain together these operations, then the group is called abelian or commutative, and that considerably signifies the underlying theory. So this is going to be like a dividing line in our discussion. And particular generalizing ideas from the abelian realm to the non-abelian realm is going to be really exciting. And it turns out that many ideas do generalize, but they become sort of somehow more subtle and lead to more insights than otherwise you might imagine. Okay, so that's just a couple of examples of groups, having started out from an abstract definition. Well, the simplest series of groups that one can think of are the so-called cyclic groups, which are essentially just the integers modulo n. So you take integers 0 to n minus 1, and then you consider addition modulo n. This structure, which you can think of as kind of these numbers sitting around the circle and adding, and you add the angles corresponding to each number, but you always come back because they're in the circle. This sort of thing is called the cyclic group of order n. The smallest group, which has slightly more interesting structure, is called the Viergruppe. It has 4 elements, and which you can call, say, 1, I, j, and k, and obeys this multiplication table. So for these small groups, one way to just capture the group is to explicitly write down the multiplication table. This is what I'm doing here, right? So if you carefully look at this, you can see that 1 is the identity element. Any element squared gives you back 1. And if you multiply any element by any other element, then you get the third element. If you carefully look at the structure, you discover that this is identical to taking the direct product of just 2 cyclic groups of order 2. So this is like moving around on the unit square. The first non-commutative group, if you kind of start charting out the groups, is the quaternion group. So this is it has 8 elements and has a slightly more complicated multiplication table. I'm not sure, can you see this? I mean, even for me, it's kind of, yeah, even at the back? All right, cool. And here the essential thing is that that the multiplication is kind of induced by this cyclic permutation of I, j, and k. So if you multiply I and j, I by j, and then you get k, j by k you get I, k by I you get j. But if you multiply them the other way around, then you get, instead of plus k, you would get minus k here. So this is the first example of a non-commutative group. Okay. Now, I started out talking about the icosahedron. The symmetry group of the icosahedron is quite famous. It's called the alternating group over 5 letters. I'm not sure, maybe in the second part of this work I'm going to say where that comes from. For our purposes, what are going to turn out to be more important are the so-called symmetric groups. So these are just the groups of permutations. Okay? So if you take n objects, and you consider all bijections of those n objects, or a set 1 to n into the set 1 to n, so all possible maps from 1 to n to 1 to n, all possible matchings. Clearly there are n factorial of them, and clearly this forms a group, right? So if you consider, or if you regard the permutation as an operation on these numbers 1 to n, a particular way in which you exchange the numbers 1 to n, and then one of these operations you can follow by another. This is what gives you the group structure. And the resulting group is called a symmetric group, denoted Sn, where n is the number of objects that you are permuting. So it might seem like this is a canonical thing. Indeed, many results in the theory of finite groups have their simplest non-trivial case for the symmetric group. But even this simple thing, just considering all permutations of something, reveals surprisingly deep and intricate structure. This is what we're going to talk about in the second half of the talk today. Okay. Now, going back to commutative groups, just integers, again with respect to addition, again form a group. This is slightly confusing, I must warn you that, right? Usually the way addition of integers is denoted is with this symbol here, right? But here in group theory land, I just said that usually we denote the group operation by multiplication. So x plus y becomes x times y. This is how I'm going to refer to x plus y. I hope it doesn't confuse you too much. Okay. So under the same identification between addition and the group operation, continuous spaces also form a group, in particular the reals and Euclidean vector spaces. So this is just the addition of vectors. That's also a group. This is our first example of a continuous group. In fact, it's a Lie group. I'll tell you more about those soon. Other examples of such continuous groups are the rotation groups. Maybe I could have put this in the context of the icosahedron again, because obviously there is a finite number of ways in which you can capture the symmetries of the icosahedron, but they come from a larger family of all possible rotations of three-dimensional space, right? So that forms a group. If you think about rotation as an operation acting on three-dimensional space, rotating it somehow, then you can combine these operations and get further operations. So again, the group axioms are satisfied. This group is called SON because it's identified with the set of orthogonal matrices of determinant positive 1 in the obvious way. Okay, so these are the Euclidean rotation groups. A slightly larger group is the group of all rigid body motions. So if you don't just take rotations, but rotations and translations, that's again a symmetry. It again forms a group. And the fact that Euclidean geometry is nothing but the study of objects in Euclidean space in a sort of invariant manner to this group led Felix Klein to make this very general statement that geometries in general can be regarded as just the study of objects invariant with respect to a particular group. So from an algebraic point of view, geometry is not, you might think that geometry is about, lines and circles and points and whatnot, but on a more abstract level, all that's happening is that you have a set of objects, you have a symmetry operation on them which is captured by a group, and you are studying the properties of the objects which are invariant with respect to that symmetry operation. Okay. Now the special unitary groups should be familiar to anybody who studied physics because they are fundamental to a modern treatment of quantum mechanics. I also must mention the general linear group, which is just the matrix of just the group of all invertible matrices of size n by n. So in some sense the rotation group is a subgroup of this group, right? Because those are just matrices which are orthogonal and have determinant 1. If you consider all possible matrices which you can invert, so which you can find the inverse, then you get the general linear group. And finally there are so you can continue this series. There are many series of groups that people have studied. There are also individual groups that are of interest for particular reasons. For example, this one, which is famous for its, which you might not otherwise study if it weren't the symmetry group of Rubik's Cube, right? So I'm not sure how many of you have tackled Rubik's Cube. I'm not sure if any of you have tried it with group theory, if you were to do that, then this is the object that you would be studying. Okay. This is not the only complicated group. Things do get a little bit hairy if you try enumerating all groups or to categorizing them and figuring out what the fundamental groups are. Famously, the largest group that is simple in some sense has been proved to be the so-called monster group, which has this many elements. Okay? So from a mathematician's point of view, what's fascinating is that groups capture this like fundamental notions of complexity, right? So it's clear that from simple structures, you can combine simple structures to get more complicated structures, right? The question is, what are the simplest, like the fundamental structures? And you start enumerating them. You find these families, like the symmetric groups. Okay, for any n, there is a symmetric group corresponding to that n. And then there are these odd ones which don't fall into any categories. So you look at those two, and you find one and the other, and they get larger and larger and more difficult to describe. You think it might never end, but it does end at a certain point, although it takes a little bit of work to describe something that is this big. It took about 100 years. All right. So that justifies at least the fearful part. Okay. So before I get into the machine learning part, let me just say how to find our way in this universe of groups of different types. So some of the groups that I talked about and some of the groups that we're going to be looking at in the machine learning context are finite groups. In many sense, they are simpler than, obviously, than the infinite and the continuous groups. So the cyclic groups, the Fier group, the quaternion group, the monster, and the symmetric groups are all finite. Now they're infinite groups, but there are but some of them are countable, so things generalize naturally to that case, such as the integers. That's fairly simple. Things get more interesting when the group becomes continuous. And the subset in which you can put a topology which matches the group structure is the Lie groups. So in the continuous group realm, people mostly focus on these groups. In particular, the rotation groups and the unitary groups fall in this category. The Euclidean groups, so the group of vectors with respect to addition, and rigid body motions are also Lie groups, but they're not compact. So that's a further distinction between structures which are compact in the topological sense and structures which are not. This distinction is going to be important to us very soon when we look at invariances. Okay. As I said, groups are just one type of algebraic structure that mathematicians study, and they do fall in this hierarchy. So groups are commutative or non-commutative, but if you further relax the axioms, you leave out the inverse axiom, then you get semigroups. If you add an extra operation, then you get rings, and if the second operation, so when you have both addition and multiplication, when they fit nicely together and both of them have inverses most of the time, then you get fields such as the real numbers and the rationals. Finally, right at the top of the hierarchy are the closed fields, like algebraically closed fields like the complex numbers. Okay. But for now, we're just going to concentrate on groups. That's going to be more than enough. Okay. So the plan for the rest of the talk, after talking about half an hour, I thought maybe I should let you know what's in store, okay, is to talk a little bit more in the general to build up our set of tools that we're going to use when we tackle learning problems. And the two key tools that we are going to resort to are representations. So I'm going to talk about representation theory, which leads to harmonic analysis. Okay, so these are the two mathematical tools that I'm going to describe, and then I'm going to go into applications. So the first application is going to be the first application is going to be capturing invariances, in particular rotation and translation invariance in vision or pattern recognition. So rotational and translational invariance. After this, I'm planning to take a short break, like 10 minutes, and in the second half of the tutorial I'm going to focus on things related to the symmetry group, in particular from the point of view of application to multi-object tracking, and later, if we have time, ranking and permutation learning problems. Okay? So, to continue with this part of the talk, now I'm going to tell you about representations. All right. So, groups are nice, abstract mathematical objects. What happens when we try and put them to work, right? So what happens when we take a group and the group is acting on a set, is really going to correspond to operations. So for example, what happens when you look at the symmetric group of over 3 letters, so the permutations of 3 objects, and identify it with the group of symmetries of the triangle in the plane, right? So that's one of the simplest things that you can think of when you're thinking about group actions. This is exactly the sort of thing as with the icosahedron, except that here we're in 2 dimensions and not 3. And here we have a much simpler structure, right? So the triangle, any permutation of the vertices is a valid permutation as far as the triangle is concerned. Okay. Now, one way to think of this operation is as just the mapping that takes this figure into itself. So this is a linear mapping from the plane to the plane. It's just a rotation or a reflection and the rotation. So you can represent it by matrices, right? So the identity group operation is going to be represented by the identity matrix because that leaves the triangle in place. If you swap vertices 1 and 2, then that's going to correspond to this 2 by 2 matrix. If you swap 1, 2, and 3 in this cyclic way, then the corresponding permutation or corresponding rotation has this matrix, and from this you can derive all the other matrices corresponding to the remaining 3 group elements. You can do the same thing for the icosahedron, obviously, but there you have 3 by 3 matrices. In the case of things like the rotation group, the group itself is defined by matrices. So there is some really simple connection between group elements and matrices, right? It's an obvious idea to associate matrices to group elements. One more example that I should say is larger permutation groups, right? There you have the permutation matrices. So these are n by n matrices, and their definition is simply that the permutation matrix corresponding to sigma at position I and j is +1 if the permutation takes the ith letter to j and 0 otherwise. Okay, so these are the classical n by n permutation matrices. In all of these cases, what happens is that you associate to each group element a matrix. So you have a map, so you can call it, say, rho, from the group G to the set of n by n real, or in more general case, complex matrices. And these matrices are going to capture the effect of the group element on something, right? So if you have one group element, say x1, and you have a corresponding matrix, rho of x1, you let that act on that something. So say u is the vector that represents your object, but then you have another transformation acting on this thing corresponding to the group element x2, then the corresponding operation is going to be just multiplication of these two matrices, right? This is what's going to happen if you first let x1 act on you and then x2 act on you. But this is, of course, this compound operation is, of course, the group element x2 times x1. And that has the corresponding matrix rho of x2, x1. Okay? So the fundamental thing that these matrices are going to have to obey by virtue of being associated with the group is this multiplicative property, that rho of x2 times rho of x1 equals rho of x2 x1. Okay? And one way to look at it is that the matrices really kind of model the group. Right? So you have a group which is this abstract mathematical object. It has a non-commutative multiplication law. The one way to make it more concrete is to associate with each group element the simplest type of mathematical object you can think of that can capture non-commutativity. And that type of object are matrices. Okay? So this is just a way of bringing groups down to earth. To each group element I associate a matrix that behaves the same way as the group elements do. Okay? This is exactly what a representation is. Oops, what happened? Okay. So a representation is a mapping from the group to the set of d by d complex matrices obeying this fundamental multiplicative law. Okay. So for example, if you do this for the quaternion group, you get out the famous Dirac matrices, which Dirac introduced in the late 1920s to model the states of spin 1/2 particles such as the electron. Okay. Okay. Now, again, when a mathematician sees structure, the question he asks is, what are the kind of fundamental types of structure, right? So here I told you that each group can have representations. You can think of many possible representations. What are the really fundamental types of representations? So one thing that you notice pretty fast is that if you take any representation, say rho 2, and you conjugate it by a matrix, then that's a cheap way of getting a new representation, right? So if I give you one representation, rho 2, then you can get this whole sequence of representations just by conjugation by matrices. And that sort of doesn't count. So representations which are related by such a similarity transformation are called equivalent. Another way to get more complicated representations from simpler ones is to just take their direct sum. Okay? So this is what is happening here. I've got two representations, rho 1 and rho 2, and I'm putting them in this block diagonal form. What I get out obviously obeys the same multiplicative relation, so it's itself a representation, even if I conjugate it by a matrix T. In this case, rho is called a reducible representation. It's clearly not fundamental in that it breaks apart into a sum of these smaller representations. What's going to be important to us are complete sets of inequivalent irreducible representations. So there is some amount of freedom in choosing this usually, because you are defining these irreducible representations modulo this equivalence relationship. So from each equivalence class you can choose which representative you want, which representation you want to take. But mathematicians spend a lot of time describing complete sets of inequivalent irreducible representations for particular groups. This is itself often a major task, and we'll see that it's important to solve this task because many things that we're going to do in the future depend on taking individual elements from such a set. Okay. Furthermore, I'm not going to explain why this is the case, but it often proves to be convenient to use unitary representations, where the inverse so the representation matrix corresponding to the inverse of an element is just the Hermitian conjugate of the matrix corresponding to the element itself. So in the following, I will always assume that our particular set of inequivalent irreducible representations consists of such unitary representations. Okay. Now, a fundamental theorem, right, very early on in representation theory, is that you can do this sort of reduction into irreducibles for any representation, and the reduction is going to be unique, of course, up to the ordering of individual terms in the decomposition. Okay? So if I give you a general representation of a group, then you can reduce it into a sum from your favorite set of inequivalent irreducible representations, and you can essentially only do it one way, right? So asking how a representation reduces into a sum of irreducibles is a well-defined question. The final trick that we need from representation theory has to do with taking direct products of representations. So that's another way in which you can get more complicated representations from simpler ones. It's easy to see that if you take two representations and just take their Kronecker product or direct product, then what you get is also a representation, but usually it's not irreducible. So you ask, how does that reduce into a sum of irreducibles? Well, there is some sequence of irreducibles that you get out, and also some matrices here which affect the right transformation, right? So this is called the Clebsch-Gordon series, and these matrices are the Clebsch-Gordon matrices. This is a famous problem in representation theory, kind of right at the beginning when you start exploring the representations of a given group, which is often surprisingly hard. So physicists will be familiar with the Clebsch-Gordon coefficients of rotation groups and SUN, so the special unitary groups, because it's central to how we deal with angular momentum in quantum mechanics. You might think that you can do the same sort of thing for other groups. It's true, you can do it, but it's much more difficult. I spent like the last weekend just computing a couple of these theories for the case of the symmetric group. It takes hours and hours, even for a relatively simple finite group like the symmetric group. And for many groups, this problem is in fact unsolved. So you've asked the kind of first non-trivial question in representation theory, and already you get something which you know as a solution, but it's surprisingly difficult. This is the kind of reasons that representation theory has occupied mathematicians for so long. Okay, so the reason that representations I think are important, representation theory is important to the way that we handle symmetries in machine learning, is because representation theory is what you need to generalize harmonic analysis into this non-commutative realm. And harmonic analysis is one of those areas of math which spans across basically the whole of the spectrum, across geometry and analysis and algebra. It's really one of those unifying concepts. So the generalization of the Fourier transform to a group is really very simple. If you think about Fourier transform on in the classical cases, say on the real line, well, it's just a weighted sum, right? If you take a function f and you take its Fourier transform at a particular frequency k, then it's going to be something like the integral over the real line of this exponential factor I kx times f of x dx. To generalize this to groups, you do something very similar. You again start out with a function on your group. So f is a function defined on the group, so general complex valued function. You sum over the group. So instead of an integral, I wrote things in this discrete language here for the sake of simplicity. So you imagine you're in a finite group, you just sum. And then you weight by something, but instead of these exponential factors, you weight by the representation matrices. And that's not such a crazy thing to do, because representation matrices obey, by definition, this multiplicative identity, you know, rho of x times rho of y equals rho of xy. That's exactly what these exponential factors obey over there. Okay? So this is saying that Fourier transformation is kind of this weighted sum by something which obeys the representation property. In particular, these exponential factors, from the algebraic point of view, they're justified in the case of the classical Fourier transforms because they are themselves representations of the translation group, right? It's just that they happen to be one-dimensional representations, so people don't normally think of them in terms of matrices. But in this case, because we're in a commutative group, it turns out that all representations are one-dimensional, and that's just what you stick in there. So this exponential thing is in fact a representation. It's just a special case of this more definition of Fourier transformation on groups. Okay. And much of the machinery from classical Fourier analysis does carry through. So for example, you have an inverse transform given by this formula, and all the classical properties that we are used to, such as of course linearity, unitarity with respect to the appropriate norms, and the translation and the convolution theorem fall out naturally. But one thing that is different, and this is important to bear in mind, is that the symmetry between the space that you start out from and the space in which the Fourier transform lives is broken. This is something that is a direct result of non-commutativity. So if you look at the formula on the previous page, right? In comes a function over the group f, and out comes something which is just a bunch of matrices, right? So this is a weighted sum of matrices. Each representation is going to have a corresponding Fourier component, and each Fourier component is going to be a matrix. So the Fourier transform is just a bunch of matrices of different sizes. So at first sight, this seems like a very different object than what you started out with, like a function on the original space. But it turns out that this is just a manifestation of a deeper duality between groups and their sets of inequivalent, irreducible representations. Okay. I was told that I should take a break after 60 minutes. I've got about 15 more minutes. That should be just about enough to finish this general part on the on the math, and then we can start with the machine learning applications in the second half of the lecture. Okay. So much for the structure of the Fourier transform. How about its properties? And in particular, I mentioned translation. What do I even mean by the translate of a function or a group? Okay. So the idea here is very simple. We have a function f going from the group to, say, the complex numbers. And if you think about, so generalizing the idea of translation on the real line, which takes, say, f into f dash, such that f dash, if you translate by z, then f dash x minus z is going to equal the original function at x. The natural definition of translating a function on a group is that the translate by z at some location x be equal to either z inverse x, so the value of function at z inverse x, or the value of the function at x z inverse. Okay. So again, non-commutative is playing tricks with us, we're going to have to distinguish between two cases here, depending on whether we translate on the left or translate on the right. But apart from that, it's a very similar kind of idea to what we had on the real line. All that happens is that what you expected to find at x is now going to happen at z of x in the translated function, or in the case of right translation, it's going to happen at xz in the translated function. And if you plug this formula into the formula for the Fourier transform, so if you try and compute the Fourier transform of such a translated function at a particular representation rho, so you write down the formula, and that's going to be a sum over x in the group of rho of x f z at x. Now for fz of x, I substitute its definition, so it's going to be f z inverse x. Okay. Now I change variables, letting y equals z inverse x. Okay. Now by the group property, summing over x is the same as summing over this new variable y. So this is going to be sum over y of rho of x, which is just going to be zx, zy with the new variable, times f of y. Okay, but now we use the definition or defining property of representations and replace this rho of zy by rho of z times rho of y. Rho of z is a constant, so it can move out in front of the summation. And we finally get that the Fourier transform of the translated function is just the Fourier transform of the original function. Sorry, the Fourier transform of the original function and the same irreducible representation, but pre-multiplied by the single representation matrix. Okay, so this is the left translation property, which is naturally inherited from the classical case. The only difference in doing things with respect to right translation is that in that case we have the representation matrix appearing on the other side. So in that case, the Fourier transform of the right translated function at rho would be the original Fourier transform multiplied from the right by the representation matrix corresponding to z. So this is nice. This generalizes naturally. Okay. So this is going to be useful in practical applications involving invariance, as we shall see in a minute. And it also leads to insights about, like deeper insights about what this whole Fourier transformation business is really. Because one way to think about Fourier transformation in the classical case is that if you take the space of all functions that you apply the Fourier transform to, so you take the space of functions, then it kind of defines it defines a way to separate that space into subspaces which are independently affected by translation, right? So when you think about classical harmonic analysis, one thing that happens is that when you take a function apart into their harmonics, then the individual harmonics are going to get multiplied by different exponential factors. This is kind of like a stratification of the space of functions into subspaces which transform independently. But here we have this added layer of complications due to the fact that left translation and right translation are not the same. Okay, and in particular, if you go back to the definition of the Fourier transform, then since it explicitly involved representations, and the definition of representations, there's this freedom of how you choose your irreducibles from possible irreducibles, so from how you actually choose the members of these equivalence classes of inequivalent irreducible representations. There is some arbitrariness in the definition of the Fourier transform as well. Okay. But this sort of property of how a function space splits into subspaces which behave independently, that's clearly a fundamental algebraic property that cannot depend on your choice of representation, right? So if instead of just looking at the definition of the Fourier transform as, you know, a way to describe a procedure, you look at it as a projection, right? You take a function, you project onto these components, and then you assemble the components according to which irreducible representation they come from. Then that captures a splitting of the original space of functions, so this space, which I denote by CG, into components which behave independently under both left and right translation. So this is a more fundamental algebraic way of looking at the Fourier transform, and it essentially amounts to setting up an isomorphism, that is like a one-to-one correspondence between two types of structure. On the one hand, it's the space of functions with respect to left and right translations. On the other hand, it's the it's just a sum of d-dimensional matrix algebras, where each matrix algebra corresponds to one of the irreducible representations. Okay. So for those of you who are familiar with the concept of group algebras, this is an isomorphism from the group algebra into a sum of irreducible group algebras, some of essentially just general linear groups. Maybe I think this would be a good time to take the break, and then immediately after the break I'll go into the applications, starting with the one in Vision, where you can see all this machinery put to work.
So how long do you want the break?
Maybe 10 minutes?
Okay, great. Questions or?
Yeah, if there are any questions so far, I know it's all been math at this point. I'd be happy to answer them. Probably it's just a repetition or a recap for many of you, maybe totally baffling to others. Okay. All right, so we're back in 10 minutes. On recently, and that directly applies those ideas that I talked about in the first part of the tutorial to real-world machine learning problems. Okay, so the first application domain I'm going to be talking about is just accounting for invariances, so getting rid of invariances. The simplest example of which is, of course, in Vision, where you have all sorts of nasty invariances, translation, rotation, and other things which are not necessarily so easy to handle. For the time being, we're going to just talk about these two, translations and rotations. And in the second half of the 1 hour, I'm going to talk about a totally different problem of representing probability distribution corresponding to matchings between objects and their tracks in multi-object tracking. Okay. So let's start with translation and rotation on invariant features for images. This whole study of invariants is an age-old problem in Vision, and it's really a very simple thing. If you consider natural scenes, or you consider data examples given to a learning machine, then often you are faced with a data set which has the objects at different locations and possibly at different locations. So here's, for example, the famous NIST data sets, but each of the digits, as you can see, appears all over the place. In this case, I randomly, intentionally rotated them, but this sort of happens in real data sets, so that you just don't have the luxury of having nice, regular, centered, and upright examples to start with. I'm sorry, could I have some more water, please? Thanks. So the question is, so if there is some way in which you could get rid of this nuisance of arbitrary translations or unknown translations and rotations coming into your data, then you could make the learning algorithm more efficient. The issue with this particular set of transformations is that each of these transformations by itself is relatively easy to account for. So if you just have translations or just have rotations, then classical tricks from signal processing, or it's just something like an alignment procedure, tends to do quite well. The problem is that when you combine translations and rotations, then you are looking at the full rigid body motion groups of R2, and that group is non-commutative. So this is easy to see. If you translate and rotate, then that's not the same as first rotating and then translating, right? So the commutativity of the individual translations and rotations is lost when you look at the entire group of translations and rotations together. So in the group theoretical language, this issue of translation and rotation invariance is just a question of invariant representations of data with respect to the rigid body motion groups, which is called ISO2+ in this case. Okay, so what do we want? How do we want to represent data? You want the representation to be fully invariant to translation and rotation, not just like little translations or something, but arbitrarily large translations and arbitrarily large rotations. But we do not want to explicitly have to do matching. So the first thing that comes to mind is, okay, we have these digits, well, let's just put them in the center and then do the learning. Or let's try and kind of figure out what the canonical position for a digit is, and then rotate it into the canonical position, and then use that rotated version as our training example. So in practice, sometimes this works, sometimes it doesn't. And the reason it doesn't work is that this matching thing is an essentially not continuous operation, right? So if something which is just on the border between two different digits, so two different interpretations, then a little perturbation of the digit can result in radically different alignments. And this sort of discontinuity, it really hurts learning algorithms. So it's a much neater and potentially much more powerful approach if you can account for the invariance algebraically without having to do matching. It's also important that the invariants be well behaved under noise. Many invariants that people in vision have been looking at suffer from the fact that they involve high order polynomials of the original data and therefore are very sensitive to perturbations. And finally, the most important thing is that you don't want to lose information. So ideally, you would want a set of invariants which is complete, in the sense that if you take just these invariants, then you can somehow reconstruct the original figure. Or if you can't explicitly reconstruct, then you still know that they correspond to a unique figure. So so there's only one possible initial data collection that a particular set of invariants corresponds to. This completeness property is, I think, the property which classical invariants in vision have the hardest time satisfying, and where group theory can really help. Okay. Now, the approach I'm going to tell you about is based on what is called the bispectrum. The bispectrum is not a very new thing. People have been looking at it for a long time, even in the classical case of representation of signals just on the real line. But people not in signal processing might not be familiar with it. So I'm going to gradually build things up from the classical case. There's no group theory in the first part, and then generalize it to the case of non-commutative groups, in particular the rigid body motion groups, and see what we get that way. Okay, so the simplest thing is to just look at functions on the cyclic group. Okay, so cyclic group of numbers 0 to n. Again, you can imagine that as the numbers sitting around the circle neatly like this. You have a function on this group, and you are looking at invariance with respect to the natural group action, translation of functions with respect to groups, with respect to this group, which is just like rotating the circle. Okay, so this is just the classical thing. If you have a signal, like a periodic signal, and you want shift invariance, where shift is interpreted in a kind of cyclically symmetric way. So what goes out one side comes back on the other side in your domain. Okay. Now, let's start with the Fourier transform, because we know this is just the Fourier transform and the discrete Fourier transform, which appropriate to this group. We know that the Fourier transform obeys this translation property, right? So the individual Fourier components behave in a simple, pre-prescribed manner on the translation. In particular, what happens here, I think I wrote it down earlier, but I erased it, is that if you have a function f, and you have its Fourier transform, f hat, but then you translate the function, so you're looking at fz, then the Fourier transform of the translated function at some frequency k is just going to be e to the I times k z of the Fourier transform of the original function. Okay? So this is nice because it immediately tells you that if you look at the power spectrum, then that's going to be invariant, right? So the power spectrum is just the modulus of the amount of power in each Fourier component, which you get by multiplying the Fourier component with its complex conjugate, and then these factors that you get from the translation immediately cancel. Okay? This is not surprising, that if you have a signal and you are not looking at the signal itself, just looking at how much energy it has in each band, then that quantity is going to be invariant with respect to translation. So this is a classical thing that people in signal processing use to capture signals in a translation invariant way. Of course, the problem with it is that knowing the power distribution of a signal tells you very little about the underlying signal. So a whole lot of information is lost. All the phase information is lost, right? So this is a very lossy type of representation of signals. And essentially the problem is just what I said before, that the phase information is lost. You want some phase information to go away because you want a single translation not to affect your representation. But you want all the relative phases to be there, right? So somehow you want to get rid of one global phase, but you want to preserve the relative phases of the different Fourier components. The natural way to do that is to start combining different Fourier components, so Fourier components corresponding to different frequencies. And this is what gives rise to the bispectrum. So the bispectrum is similar to the power spectrum, except that this is a cubic thing in the original signal, and it explicitly couples the different frequencies. Okay? So this will stop the relative phase information from going away, right? Because you are still doing this complex conjugation thing, and the exponential factors coming from translation are still going to cancel for that reason. But because you're explicitly coupling different Fourier frequencies, you're going to be retaining at least some of the relative phases. The interesting thing is that it turns out that you retain all the information. So if you compute all possible bispectral components, you let K1 and K2 independently range over their possible values, then this thing is going to be a complete translationally invariant representation of the original signal. So this has been known in signal processing for a while, and it's had a number of applications. In particular, people have looked at using it to represent invariances in vision. With some modifications, it can capture scaling and rotation. People have used it for rotation and for translation, but people haven't really put these different types of transformations together, because whenever you try to use the classical bispectrum, you're always limited to the translation group or in general, abelian groups, right? So as long as you have just one of these constituent transformations, such as rotation or translation or scaling, then all this classical theory from signal processing works just fine. So this is the paper on shift and rotation invariant reconstruction, but again, it's either shift or rotation invariant. Actually, this sort of thing is quite useful in time series analysis, like EKG and EEG signals. People actually use this sort of representation when they want to recognize patterns and that sort of thing. Again, what we're interested in is generalizing this theory to the case of non-commutative groups, for such as translation and rotation together. Okay. And this leads us to non-commutative bispectrum. So the idea is that what drives classical bispectra is still present in the non-commutative case, right? So when we talked about the general properties of harmonic analysis on groups, we saw something very similar to what we have there, except that now, of course, we are dealing with matrices. Okay? But modulo this fact, we can at least propose a theory of power spectra and bispectra, even on non-commutative groups. So, for example, we can write down a power spectrum in this form, which is just the product of the Fourier transform matrices with their complex conjugates. And by the translation property, it's going to be invariant. So again, maybe I should remind you that under left translation, so the setting here is that we have a function on a general group to say the complex numbers. Then we take its Fourier transform, which is going to be a bunch of matrices indexed by the irreducible representations. And we know that if we translate the function, then the effect on the Fourier transform is going to be left multiplying this by representation matrices. Okay. So just as in the Euclidean case, if we take the Fourier matrices and multiply them by their complex, by their Hermitian conjugates, then, and call this the power spectrum. What letter did I use there? Q. Then the power spectrum of a translated function is going to be the same, except that we have these representation matrices appearing. Okay, it's been the same as of the original function, but we have the representation matrices appearing. And then, provided that we've started out with unitary representations in our set of irreducible inequivalent representations, the representation matrices will cancel, and we see that the power spectrum is invariant. But again, we lose a lot of information, because if you take a matrix and multiply it by its Hermitian conjugate, then you necessarily get a positive definite matrix. So these positive definite matrices can't possibly capture everything about the original Fourier transform. The question is, how do we generalize this? How do we generalize the concept of bispectrum? So how do we now couple the different non-commutative Fourier components together? So we start out trying to do something very similar as in the Euclidean case. We know that we're going to be looking at cubic things in the original signal. So we are going to try and combine 3 Fourier components and not just 2 to form the bispectrum, and think about how to get the same sort of cancellation in the under translation as we had in the original bispectrum. So how do we combine 3 Fourier components now in such a way that their combination is going to be invariant, and in such a way that it also captures all the relative phase information? So now that we have completeness on a non-commutative group now. In the classical case, we just multiply together the first 2 components, right? So in the classical bispectrum, it looked like one Fourier component at K1 times another Fourier component at K2. These 2 were conjugated, multiplied by Fourier component at K1 plus K2. And this was nice because these 2 together behaved in a complementary way to this, right? Individual Fourier components behave in a well-prescribed fashion under translation, and then their product behaved well too. Now if we take these matrices now, Fourier matrices in the non-commutative case, and just do ordinary matrix multiplication, unfortunately that's not going to do the trick. That's not going to transform in any simple way. Instead we have to take the direct product, because again the direct product of representations is again a representation. So the direct product of Fourier components is going to transform according to the corresponding direct product of representation matrices. Okay? So on the one side we're going to have this direct product of Fourier matrices. The question is, what do we multiply that with on the other side so as to get invariance? And this is the same sort of problem as we had just before the break, or just before we went into harmonic analysis in the first half of the tutorial. This is how to decompose this direct product into individual representations. So this is the question of how to take the 2 representations rho 1 and rho 2, multiply them together, and then decompose them into sum of irreducibles. Okay. And we know that this always exists. It might be difficult to compute, but since this is just a representation, and we know that representations are always reducible into sum of irreducibles, we know that some matrices C, like constant matrices, will exist, and some sequence of irreducibles here exist such that this holds for any x. We can just like take out a big book from representation theory from library, look up the corresponding Clebsch-Gordon series and Clebsch-Gordon coefficients, and plug them into a formula. Okay? So this combination, where you take the direct product of 2 Fourier transform matrices, then conjugate them by the appropriate Clebsch-Gordon matrices and multiply them by the appropriate sum of Fourier matrices on the other side, this is the natural generalization of the bispectrum to non-commutative groups. People are aware of this, but it's not widely known, especially not widely known in applied communities. It's also sort of interesting to note that that this does become quite a large object, right? So even in the original classical case, what we had was that the original Fourier transform was obviously of the same size as the original signal, but if the original signal was, say, on the numbers 0 to n minus 1, it was like an n-dimensional vector, but the bispectrum was an n-squared dimensional object. Right? So it's larger. You have completeness, but there's a price to pay. The bispectrum is also larger, but the individual components are very large as well, because here you're taking representation matrices, are taking their Kronecker product, right? So the individual, not only do we sum twice over the set of inequivalent irreducible representations, we also form rather large matrices that will contain these invariants. Anyway, the interesting thing, and by no means trivial thing, is that the completeness property survives in this case for all compact groups and even some exceptional non-compact groups. So this was a major result that was proved by Hackerala in his thesis in the mid-90s. And then I think it kind of sort of remained on the fringes of mathematics, because applied communities were not necessarily reading the non-commutative harmonic analysis literature. Mathematicians did not necessarily see how this links up with the deep problems in pure mathematics, and not very many people use this thing. But I think this is a really powerful and deep result. Whereas the generalization of the bispectrum to the non-commutative realm is relatively straightforward. So as I just tried to explain to you, it sort of does follow the general logic of how you do things when you go from ordinary harmonic analysis to non-commutative harmonic analysis. Proving this theorem is actually not trivial. It goes quite deep into representation theory and exploits the kind of duality between groups and their sets of inequivalently reducible representations. I also have to say that there is one condition on in the theorem which at first sight is innocuous and has a direct analog in the classical case, and that is that the theorem, the completeness part of the theorem, only works if the original spectrum is non-singular. So each matrix in the original Fourier transform has to be invertible. Okay? So in that sort of set of functions of measure 0, where one of those matrices disappears or becomes singular, the invariance property still holds, because that just depends on the straightforward algebra that we went through. The uniqueness thing fails. Okay? So that's important to bear in mind when we try and apply this result in real problems. In particular, it's important when we try and apply it in problems when the original function is not really on a group, but on something that the group is acting on. So these are what are called homogeneous spaces. This is where we put the stuff to work, right? So what is the kind of context in which this non-commutative bispectra and Caccarellas results are going to be useful in practical problems? Well, the sort of things that I have in mind are things like functions on a sphere, and thinking about what happens to them when we rotate the sphere. Okay? So consider the two-sphere, which is just the ordinary unit sphere in three-dimensional space, and consider that we have a function, let's say a complex valued function on this sphere. Now if you look at SO3, so the group of three-dimensional rotations, then that acts naturally in the sphere, rotating the sphere and rotating the function with it. Right? What's interesting is to develop a sequence of invariants for such functions, which are going to be invariant to this action, so the action of the rotation group on the sphere. Now, it's clear that the sphere and the rotation group are somehow related, but they're not the same thing. So here, the function is not on the rotation group, it's on the sphere. Okay? And that is an important distinction. What's happening here in mathematical terms is that we have a function not on the group, but on what is called the homogeneous space of a group. And by homogeneous space is basically any space on which a group acts. So clearly, if you have a point on the sphere, then the rotation group takes it somewhere on the sphere. And also, the other requirement is that the entire space has to be swept out by the action of the group, which is again trivially satisfied in the case of the sphere in SO3, right? So you have the sphere, you have a point on it, say you start with the North Pole, this is your XO, and then you consider you have rotation matrices acting on this point XO, then you get other points on the sphere, and this way you can sweep out the entire sphere. So you can get anywhere on the sphere just by rotating any single point that you start out with. Okay, so this is what a homogeneous space is. And it turns out that this whole business of Fourier transformation naturally generalizes to this realm, because when you take the all you have to do is to choose a single sort of initial element, such as the North Pole in this case, and you can immediately write down a corresponding Fourier transform on the homogeneous space. So in the case of the sphere, what you get is that the Fourier transform of this function on the sphere at the representation rho is going to be the integral of, again, the representation matrices of, the integral over the rotation group, so integral over rotations of the representation matrices multiplied by the function, but of course you can't evaluate the function at rotations because the function is not on rotation, it's on the sphere. So the function evaluated at this point which you get by rotating your starting element by r. Okay. So homogeneous spaces are kind of a natural construction, and once you know the theory of harmonic analysis on a group, you automatically have a theory of harmonic analysis on all its homogeneous spaces just by this formula. And translations on the homogeneous space correspond in a natural way to translations on the original group. So everything that I said before, including the bispectrum and Caccarel's result, does carry through. Okay? So we can construct rotation invariance on the sphere. We have a function on the sphere. We form the Fourier transform given by that. From that we form the bispectrum, and we get out a bunch of numbers which are going to be invariant to rotating the sphere. This is something that's potentially really useful in all sorts of applications involving rotational invariance. Now, there is a catch, and the catch is that in this sort of context, when you have homogeneous spaces, the singularity condition might be violated. So it seems, at first sight, this seems innocuous, this business of the matrices not being singular in the Fourier transform. It turns out that when you do this sort of integral, so when you kind of mod out by something and work on homogeneous spaces as opposed to groups originally, typically what happens is that at least some of the components do become singular. So things become more complicated because the real power of the bispectrum, you have to do a bit more work to get. Okay. So this is just a graphical representation of all the rotations acting on the sphere. Okay. So this is all nice and known. Let's get back to our problem of constructing rotation and translation invariance. Okay. How do we link up what we know about invariance with respect to the action of compact groups on, say, something like the sphere, to our original problem of invariance with respect to translation and rotation in the plane? The reason we can't directly apply the bispectrum and Caccarel's result to this case is that the group of rigid body motions is not compact. Right? So that means that both the whole representation theory becomes unpleasantly complicated, and also this completeness result is something that we can't prove. The idea that we came up with about a year ago is to establish an isomorphism between these two types of problems, at least a local isomorphism. So to establish a connection between what we want, which is translation and rotation invariance on the plane, and what we have, which is rotation invariance on the sphere in R3. And the connection is really not that complicated. So if you think about what happens when you project your image onto the sphere, in the kind of any way, but the most simple way that you can think of, just projecting vertically down by the z-axis. And then you think about what happens to this projected image when you subject the original image to your transformations. So things like translation this way, and translation that way, and rotations. Then you discover that Effectively, what's going to be happening in the sphere is just three-dimensional rotations in R3, right? So this is like modeling a non-compact problem locally by a compact problem in one dimension higher. Okay. So this is all that it takes to reduce the original non-compact problem of rotations and translations into the classical problem of rotation symmetry on the sphere. And we can push through all the bispectral machinery. So first we project. We start with an initial image, say H, and we project down onto the sphere in this kind of simple-minded way. Yeah.
R and theta are coordinates of the image, or?
Yeah. So this is just the particular way in which I choose to project. The simplest way is to express it in polar coordinates. So we have to parameterize the sphere somehow, and the easiest way to parameterize it is in terms of spherical polars. Then if we want to project, the easiest way to set up the correspondence is if we start out with polars in the first place. Okay? So we start out with an image in R2 parameterized in polar coordinates. We project down onto the sphere, and then we take the Fourier transform. If you think about, if you look into it a little bit and figure out what Fourier transformation on the sphere actually means, it turns out that all it boils down to is taking the spherical harmonic expansion. Okay? So these things, these matrices coming out of there, are going to be put together from the ordinary spherical harmonic coefficients of our projected image. And then we form the bispectrum, which is the definition of the spherical harmonics. This is what like a particular projected image of a 2 looks like on the NIST data set. So the bispectrum is just going to be these set of cubic polynomials in the spherical harmonic coefficients. One thing that I kind of shoved under the carpet in the process is how what started as a bunch of matrices there became vectors over here. So if you look carefully at this, what happens is that okay, so there's if you know something about the theory of spherical harmonics, then you know that they are indexed by two numbers. The L, which is like the major index, and M, which is the minor index. The L's turn out to correspond to the irreducible representations. So the irreducible representations of the symmetry group turn out to come in this sequence, indexed by just integers. And L corresponds to exactly that number, like which representation in the sequence you're looking at. The M corresponds to the row index. So what happened to the column index? And what happened is that in these matrices, because we're now on the sphere and not on the rotation group, only one of the columns of each matrix is actually going to be active. So the reason that the spherical harmonic expansion only has 2 indices and not 3 is that each of the Fourier matrices on the sphere is going to have only one non-zero column. So this is just a specialization of the general theory into this case where each matrix is really just a vector, and that makes things much simpler. So actually the number of invariants you end up with only goes with a 3/2 power of your original data, and the amount of time that you need to compute the sums is not that bad either. It goes with the 5/2 power. Okay? So again, from an algorithmic point of view, what happens is that you start out with, say, by an n by n image that's n squared, like the size of the data originally is n squared. This is what I call U. Then you project onto the sphere, and then you choose a parameter, like how many Fourier coefficients on the sphere do I wish to maintain, right? This is something that you have to tune. This is a compromise between complexity and computation time. But if you want something reasonable, it should be something that grows linearly with n, right? So I assume that you take something on the order of 2n or 3n or something like that. And that will lead to an algorithm which has a complexity of 5/2, and the size of your invariant representation goes with the 3/2 power of the original data. So this is something that's, of course it takes time, but it's doable. In the case of the NIST digits that I actually tried this out on, I started out with 30 by 30 images. I actually used quite a rough representation, so I think I only went up to 15 Fourier coefficients. Doing that, like on my desktop machine, it only took about 1/10 of a second to process each image. To do the whole Fourier expansion bispectrum business, the invariant data wasn't too large and didn't cause any problems with that. And the results, well, compared to not taking the invariance account, they were really spectacular. So in this case of perturbed data, if you take only a few number of training examples, then obviously what you can do is, without knowing about invariance, is very limited. I started with a training set where I had about 50 examples from each class. There were 10 classes corresponding to the 10 digits. And then I tried to distinguish between them pairwise, so say distinguish between 2s and 7s. But I only had 52s and 57s, and they were all over the place and rotated and whatnot. So the baseline algorithm that I tried really didn't do very well on most of these problems. This is on the left axis, you have error. So you don't expect to have more than 50% error on binary classification task. But many of the cases, so many combinations of digits were actually right up there, saying that basically the classical algorithm couldn't handle this sort of data at all. Whereas if you do take the invariance account, if you use these bispectral features, then you get error always, or most of the time, under 15%. In many cases, you can just nail the problem completely. So for example, if I seem to remember, like zeros versus ones, that sort of thing you can learn perfectly just by using these bispectral features. So this was quite nice because I literally only took this straight out of the box. I didn't tweak any parameters, anything, just pushed it straight into an SVM on these binary classification tasks. And at the beginning, I had all sorts of doubts about this invariance, because it's fine to have things which are invariant, but also you want to worry about sensitivity to noise and how they scale with respect to each other. It seems like this sort of thing, at least in the two-dimensional pattern recognition case, is really robust. I should also say that there are natural extensions. So one of the things I'm working on is extending this to higher dimensions. So similar sort of projection tricks and so on work in 3 dimensions and higher, where invariance might be even more crucial. And also extending it to different groups of different transformations. This is, I think, even more interesting. My general sense is that although people in vision are interested in translation and rotation, they would be much more interested in scaling, for example. That it's not so obvious which group to use and how to choose the projection, but there are certainly things that one might try. So what I'm trying to convey is that there is a general kind of logic behind this thing, right? There's the projection trick, so there's the group theoretic view of problems, and there's also just the sheer power of the bispectrum, which can be unleashed in a whole series of problems. It's also interesting to look at, so the one thing that people in vision are interested in is what a learning algorithm really picks up on. So once I did the projection, I tried looking at the principal axes in bispectrum space of the original data. This is something that actually my advisor Tony Chapara did, to try to invert the bispectrum and figure out what the main axes of variation in bispectrum space are. If you map that back into the space of original images, what kind of features you get out. And so in this case, we trained the algorithm on 6s. So it's reassuring that the mean image, which is in the middle here, is kind of a canonical 6, sitting nicely in the middle and everything. And it's interesting to see that, like, the principal axis of variation, like this one, captures something really weird. So there's some sort of twirl or something happening to the image. It's much more, well, if you contrast that with what people get at with, say, the eigenimages methods that are quite fashionable, this is something a little bit more intriguing and potentially captures more subtle variation in the data than the kind of Gabor filters, things that people pick up.
So when people do this sort of thing on regular images, what they tend to capture is, like, they capture things like translations, for example, which they were trying to get rid of, but
yeah.
So here you won't see that because this representation is invariant.
Yeah, that's exactly the point. Yeah. So if you think about what these little Gabor things are, or what their real nature is when people pick them up, it's really just a manifestation of a local translation. Like, it's just saying that that thing could be a little bit to the left or could be a little bit right, whereas this is a more interesting type of variation in the image. Okay. All right, so this was one part. The other part's in a different presentation. Unfortunately, it seems like we're quite limited in time. How much more time do I have? Sorry.
So I mean, we should really finish off in the next 10 minutes. Do you want to tell us a little bit about what the other applications, but then leave some time for questions?
Yeah. Okay. So I can at least try and tell you what I wanted to go through from my ICML tutorial earlier in the year, but without going into any of the details. Okay. So the second part would have been about, so this was about invariance, and that was in the continuous land. This was on Lie groups, rotation groups, whatnot. The other part of the application section would have focused on particular finite groups, in particular the symmetric group and its connection to tracking. Now this is interesting because there is an inherent matching problem when you're trying to track multiple objects, and its solution is by no means trivial. What happens is that, say you're a radar operator and you have aircraft on your radar, but you have limited knowledge about their identities. So what you see are these blobs, or blips, right? So as time progresses, you see something going like that. And if you have just one thing on your screen, then it's pretty obvious that this is a single object that's traversing your domain, right? Well, if you have two objects and they are nicely separated, then you also know what to do. But things get more complicated when, for example, they meet. And people have devised all sorts of methods to deal with this sort of thing, to decide whether, this is what really happened, so the two objects really crossed, or what happened was that they just came close to each other and then separated. One thing that people do is to exploit as much of the dynamics as possible. So if the things were going this way and the other one was going that way, and you know that these are aircraft, and it's pretty obvious that they didn't suddenly make a turn here. One of them simply just went this way, one of them the other way. So this is like the Kalman filter way. That's one part of the solution. The other part of the solution is just about maintaining a distribution over all possible matchings. So this is like maintaining a distribution over n factorial possibilities, or maintaining a distribution over the symmetric group. And obviously the difficulty there is that the symmetric groups just become so huge, right? So this is something that you can do explicitly for, say, n equals 3, 4, 5, 6, maybe up to n equals 10. But beyond 10, things, even on relatively large computers, things become difficult, and beyond n equals 13, it becomes hopeless. In typical applications, or in many applications, such as when you're tracking people, or you're moving around in some environment, you have different sensor inputs, you're trying to keep track of their identities, or you're tracking animals in the wild, or you're tracking particles in a particle accelerator in physics. Objects might be in the 20s, 30s, or even in the hundreds. So there's a whole literature of how to solve this association problem in multi-object tracking. And what people usually use is just an n by n matrix of kind of marginal probabilities. So they keep track of this matching matrix, say M, where Mij is somehow related to the probability of object I being at track J. But clearly an n by n matrix is very far from capturing something about this n factorial dimensional probability distribution. And the insights from the symmetric group allow you to go beyond this approximation. So if you start looking at distributions on the symmetric group and their Fourier transforms, you can identify the different Fourier components with X like added layers of complexity, just as in the case of classical Fourier transforms, where people, in the interest of computational efficiency, stick to the low frequency modes. So it's going to be a noise process, which is going to prescribe some sort of ordering of the Fourier coefficients, and in that case, it's going to make sense to transfer this tracking problem into the Fourier domain and only maintain the first few coefficients. Now, a lot of the actual technology behind realizing this, which we did about a year ago, lies in the realm of fast Fourier transforms on the symmetric group. So not only are you interested in restricting your representation of distributions over the symmetric group to this limited set, you also have to really worry about how to efficiently update the distribution and how to read off information from the distribution. And to do that, you have to dig into the literature on fast Fourier transforms on symmetric groups, which is a relatively recent field. So most of this part of the talk would have been on just describing these representations and describing the fast Fourier transform. Unfortunately, there's no way that I can go through all of that in the remaining 3 minutes. Maybe just to convey a couple of ideas. One is kind of what these how this sequence of matrices goes. So, okay, we have this n factorial dimensional group of size n factorial, which has this very particular structure related to permutations. What on earth are the irreducible representations? Okay. How do you number them, whatever? How do you keep track of them? Well, it turns out that the symmetric group over n letters is going to have as many inequivalent irreducible representations as there are ways of taking n squares and laying them down in these little Tetris shapes called tableaux. So, for example, for n equals 5, you have 5 boxes in which you want to put down in consecutive rows, and the rule is always that rows have to start at the left, and no row can be longer than the one above it. So, for example, this is one of these valid so-called Young diagrams. So there's going to be an irreducible representation corresponding to that. Now, another one might be this one. So it's going to be an irreducible corresponding to that. But doing this, that's not a valid Young diagram, so that doesn't come into the sequence. Okay? So when I was trying to do multi-object tracking with harmonic analysis of the symmetric group, I had this sequence of irreducible representations, all indexed by these Young diagrams. And then it turns out that the shape of the Young diagram somehow corresponds to the frequency. So in general, the kind of long flat ones are the low frequency modes. So this is how it starts. This is in the case of n equals 4. Let's skip to the next slide. Yeah. In general, this is the sort of thing that happens, that you have a one-dimensional representation corresponding to the long flat one. That's really uninteresting because this is the constant representation, the trivial representation. So that's just like the sum over all elements in the symmetric group. Then you have an n-1 dimensional representation, or n-1 dimensional Fourier component corresponding to that thing. Then the next one is n times n-3 over 2 corresponding to this sort of shape, and so on. And when you want to do some sort of approximate probabilistic inference on the symmetric group, the question is where you cut off this sequence. So it makes sense to cut it off when the power jumps, right? So you can keep the first two, and that would be equivalent to doing the classical thing of just maintaining an n by n matrix. Then if you can afford to, then you also maintain the quadratic representations, so they're going to be n squared by n squared matrices. There's the next two irreducible representations. If you can go beyond that, then you can keep track of the cubic ones. There are 3 of those, but pretty soon you have to cut off. Okay, but at least you've got some flexibility over how much representational power you can allow yourself in your algorithm. And then there is the then there is this update procedure, which is close related to the Fourier transform. And so this is combinatorial representation theory. It's the sort of thing that mathematicians love, because it turns out that the structure of these matrices, it's all related to how you can play around with these tableau, and this is fun. So you can worry about how to take boxes away from tableau and how they reduce into tableau corresponding representations of smaller groups and so on. That's what ultimately leads to the form of the Fourier transform. This is again one of these games, like building up tableau by adding boxes. This is great fun. Okay, maybe I can just show you some results. This is going to take forever. So, skipping to the end. Yeah, this is the package. So I actually had to write my own code for doing all this transformation, because apparently, although the Fourier transform has been known for a decade, nobody has bothered to code it up. In the tracking case, we had a noise model, which was just a model saying that, for any pair of tracks, there's the same probability of the corresponding objects or targets being exchanged. Inference was this kind of online Bayesian thing, where you had the noise model operating in the background, but when you actually observed one of the targets at one of the locations, then you updated the probability distribution in the obvious way by Bayes' rule, and that turns out to be easy to implement using the fast Fourier transform. And the results, well, of course we got better results than people just using an n by n matrix, because our whole method had more power, right? We're keeping track of more information. In fact, you can even see that the more representation matrices we have, of course, the better we do. So in general, the trend is that with increasing number of representations, the methods get more powerful. What was interesting is how far this sort of thing could be pushed. So even though we are not doing n factorial work, these matrices do grow pretty fast, and that sets a limit in n. So beyond n equals 30, even the n squared by n squared matrices become a little bit too much for regular computers to maintain. So this sort of method is really useful in the intermediate range of, say, n equals 10 to 30, where you can't afford to keep track of the exact distribution, but you can still keep track of at least the n cubed and the n squared, or just the n squared representations. And there, I'm not sure if you can see the baseline on these plots, but there was significant improvement over a baseline method. All right, I'm sorry I had to cut it so short at the end. I still hope that it gave you some flavor of why machine learning might benefit from some ideas from representation theory.
Great, thanks. So if people have to leave, feel free to do so, but we should take some time for questions as well.
Yeah? Sorry, over there? One.
I can understand why your dimensionality goes up when you do this, when you get in these extra features, because I would think if you're getting rid of some of the information, so you're getting rid of the translation and
oh yeah,
factors, then your dimensionality should be going down.
yeah, but this is an over-complete representation, unfortunately.
Could you repeat the question?
Oh yes, sure. So the question is, why on earth does the dimensionality of the representation of a data instance go up when what we are doing is getting rid of some invariants, right? So if we get rid of some like nuisance information in the data, then presumably the actual size of the data should go down. But unfortunately, this is not the case. So these are over-complete representations. I can only prove, or Caccarel can only prove his theorem for the entire bispectrum, but clearly there is some redundancy in there. It's not necessarily easy to pry out where the redundancy is. In fact, in the case of the Euclidean, of just translations on the real line, in the classical case, you can tell you can find a subset of the components which are sufficient for completeness. So that's nice. In fact, the diagonal, the off diagonal, like off from the diagonal off by one elements in this thing, it's sufficient to reconstruct the whole thing. But on general groups, it's not so easy to see what you can throw out and what you can't. So you are stuck with the entire thing. Yes?
The singularity issue,
Yeah.
the three-phase space is more generally kind of a curved space.
Yeah.
So I'm sure you mentioned, but probably I missed it. So the singularity is going to be ineffective. So how are you going to deal with it? Are you just using a badge, writing the mannequins, or are you working using some sort of a trick?
So if the original function is on the group itself, then the singularity issue is not such a great problem because you're unlikely to end up in one of these singular locations. Even there, if you are trying to do something like use a Gaussian process for regression, it might be a problem that your space is kind of stitched up, like certain parts of the space that really appear as the same. That's really good. We're trying to run experiments with this. We have various applications in which we're exploring, and we'll see how serious a problem that is. And it seemed like for the digits, it wasn't an issue at all. I mean, this worked just fine. But if you're at a singularity, what to do, that's a different matter. And I'm trying to, so there might be ways of getting around this. I'm trying to figure it out right now. But I think that's one of the most interesting questions in this whole realm. So Caccarelli wrote the whole thing about functions on groups in general, and this was just like a minor condition in his theorem. I think that's where, in terms of theory, that's part of that's one of those places where there's real interest in figuring out what to do with the singularities.
Well, I think you manage that. It would be kind of a breakthrough because this is so common in general relativity and particle physics. Like, I mean, we're curved space, so if you can deal with that.
Yeah. I hope it doesn't take solving a general problem from general relativity to figure out what to do with this. Hope it's not as bad as that. Yeah.